In this video, we are going to learn about RLC circuit, which is the last topic in Unit 2. So far, you have learned about the behavior of capacitors, the behavior of inductors, and an RL circuit and an RC circuit. The last topic is about RLC circuit. So these are the topics which is going to be covered in this video. So before getting into the RLC circuit, let us review about your first order system, what you have studied before. So when we say it is a first order circuit, when a circuit contains one energy storing device, either a capacitor or an inductor, along with our resistor. So you have already seen RC circuit and RL circuit. It is called a source-free circuit. Why? The capacitor or the inductor stores the energy when they are connected to the supply. Once the source is removed, they become source-free. The energy stored in the capacitor or in the inductor will be given out and the circuit works on it. So by applying a KVL to your RC circuit, we try to find out the voltage given out by the capacitor, which is V of t is equal to V naught e power minus t by tau. V naught is the initial energy stored in your capacitor and tau is the time constant. So all these you know well. And the energy, the voltage given out by the capacitor is being shown in this graph. Same thing when we come to an RL circuit, again KVL is applied, we got the current equation, and you know this is the current given out by the inductor. The inductor stores the magnetic field in terms of current, and this curve say is the current given out by the inductor. So now we are moving into the second order circuit, which is our RLC. Why it is called a second order? As it contains two energy storing devices. Two energy, it means they are two different energy storing devices. It's not the same, not two capacitors or not two inductors. Here we have capacitor as well as an inductor. So when we write a voltage equation or a current equation using these RLC circuit, we'll get a equation of order 2. So that's why it is named as second order circuit. So let us get inside. So again, the second order circuits are classified into two types: series RLC circuit and parallel RLC circuit. So in series RLC circuit, the equation is going to be a current equation. Why? Because the current will be same in series circuit. In the case of parallel RLC circuit, it's going to be a voltage equation V of t, where the voltage will be same in parallel circuits. So let us take a series RLC circuit. So the response, the source-free response is otherwise called as a natural response, as you've seen earlier in RL and RC circuit. So this circuit get excited or it starts working because of the energy stored in these two energy storing devices, the inductor, the capacitor. So since it's a second order circuit, when we apply a KVL, we'll get a equation of order 2. So see, it's also current here, di and I. So the equation is going to be a current equation When we solve a differential equation, we'll get our solution. So since the derivation is not required as much, we are just going to see the equation. When we solve, we'll get this. So here, this we have to know about two constants. One is an alpha and another one is an omega naught. Alpha is the Neper frequency or a damping factor, and omega naught is the resonant frequency. So later we'll get into it once we discuss this topic again in the session. Why it is called a Neper and why it is said to be a resonant frequency. Else you guys dig into this concept and collect the information about it. What is a Neper and what is the resonant frequency? So this is called as the characteristic equation after substituting this alpha and omega naught. So this equation decides the nature of our RLC circuit. The RLC circuit behaves in three ways. So that behavior we can understand or we can come to know by this characteristic equation. So let's see what are those three categories. When our alpha value is greater than omega naught, the value of alpha is greater than omega naught, it is said to be overdamped. When these two values are same, then it is called critically damped. When alpha is less than omega naught, it is said to be underdamped. We can visualize this by the graphs. See, this is the overdamped case, which is normally happens, and even critically damped also is a smooth conduction. The circuit works smoothly. Underdamped is a condition which we avoid in every circuits. When we design it, we have to look into the values and we have to design in such a manner our circuit should fall into these two categories, overdamped and critically damped. Underdamped case should not occur in the electrical circuits because these leads to oscillations. There will be fluctuations happening in a circuit. Such condition is an underdamped one. So when we design it, it should be carefully designed that it should not fall under this category. So whether it is a series RLC circuit or a parallel RLC circuit. So when we put together all these concepts which is seen over here in the table. So all the three conditions are applicable to your parallel RLC also. And their responses. See, these equations are current equations for series RLC circuit, and when it comes to parallel RLC, the equations are voltages. The only difference between your series and parallel is your alpha value. Alpha is R by 2L here, and in parallel alpha is 1 by 2 RC. So this is, with this, our RLC circuit concept is getting over. We'll see the problems in the class and we discuss about some more concepts in the class.